Good morning, everyone. Today we will start chapter 5, and from the first section, we are going to looking at the areas between two curves. In the chapter 4, we studied how to find the area under one function curve. Now we are looking at the areas between two functions f and g. Now let's consider the region in this way. Let's consider the region S. The region S that lies below the function that lies between two curves y equals fx and y equals gx, and between two vertical lines x equals a, x equals b, where f and g are continuous function, and we assume f is greater than and equal to g for all the x defined in the domain. So let me give you the function here. So I'm going to draw the two functions f and g in the xy plane. So this is my function f. This is my function g. Okay, so this is f, this is g, and my a here and b. So from this graph, so this is the case 1. Here, both f and g are positive functions. Okay, for all x starting from a to b. Okay, for all x in AB, my function f g, let me write in this way. Okay, so both are positive. Okay, f is positive, g is also positive, and we know that from a to b, my function f is greater than function g, right? My function f is greater than function g for x in the AB. So we are interested in the area between f and g, So let me shade it the area we are interested. So we are interested in the area between f and g from A and B. How can we represent this region S? So this region S will consist of all the points which can be represented as the coordinate x and y. So my x starting from A to B, right? My x is between A and B can equal to the endpoint. And what is my y? My y should be between the gx. This one, the bottom one is the g, okay, is g, and the top one is the function f. So my y is between the gx and fx when my x is between A and B. So here it's similar idea. Okay, it's similar idea. We are interested in the area of this region S, right? In the area of this region S. So what can we do? We can cut this region into n strips, and we are going to use the approximating rectangles to estimate the area of this region S. Okay, now let me write in a more clear way. So to explain the idea, okay, to explain the idea. And this is the case 1 I called, okay, case 1. Let me change a little bit, tiny. Okay, then let's show the region again. So my function f, my function g, they do have some intersection, but it doesn't matter. Between a and b, the function f is always greater than function g. Okay. So this is from a to b. This is my function f. This is g. But from a to b, function f is greater than function g. X, O, Y. Now to estimate the area of this region S, then we are going to divide it into n strips, right? N strips. Now let's look at the I strip, okay? Now let's look at the I strip. I just zoom in, okay? Let me zoom in this part. And again, those endpoint, we can call it xi minus 1 to xi, okay? Xi minus 1 to xi. And then we need to estimate this region, right? Let me erase this part. So for the region Si, this is the region Si. Right? To estimate the area of the region Si, we can use a rectangle to estimate the area of the region Si. Right? So using a rectangle to estimate the area of region Si. And we know the Si, we have the subinterval is xi minus 1 to xi. And here we still have the equal weights for each rectangle. Equal weights, how can we work out the formula for the equal weights? From A to B, we have n strips, okay? N strips, so the equal weights is the same. Delta x equals b minus a over n, right? We still have the n subintervals, okay? N subintervals. Now we need to figure out the height of the rectangle, okay? The height of the rectangle. The height of the rectangle. And besides the left endpoint, right endpoint, what is the common choice? What is the common choice for the height, for the choice of height of rectangles? So here, to estimate the area of the region S, you can use the rectangle, okay? You can choose a rectangle. And we can we understand that this is the height, this is the weights, right? This is the weights of the rectangle, which is delta x. But how can we form the height, okay? How can we form the height? So I can choose the height at xi star. So I will call this point is xi star, which is the sample point in the ice interval. And we understand sample point is the free choice in the ice subinterval, right? Any value between xi minus 1 to xi. So this height, then we can form a rectangle's height in this way. So this is a rectangle showed shaded in the red color, okay, in the red color. Now we need to figure out what is the height. What is the height of these rectangles? So here, this one, this is when the x values is xi star. So what is we need to figure out this part, right? This part that gives the height of the ice rectangle. But what is the value here? This value should be when x is xi star, the function value on the function f. So that will be f xi star. Xi star. And what is the function value here? This is when x is xi star, the function value at the curve G. So this value will be G xi star. Make sense? Now here the height for the rectangle is not just the one function value again. It's not, okay? It's not the value of one function. It's not like fxi star times delta x. Now the height becomes the difference actually, right? The difference, this point is fxi star, this point is gxi star, and we are interested, the height actually is the difference between those two function value, which is this part. So the height now, the height of the rectangle becomes the difference of the two functions at the xi star. So the height will be xi star minus gxi star. That is the height of the ice approximating rectangles. Then we can write the area, okay? The area of the ice rectangle, right? The area for the ice rectangle will be the area of the ice approximating rectangles, which is used to estimate the area of the region, SI. The area of the ice approximating rectangle is height fxi star minus gxi star. Gxi star, that is the height, then times delta x, right? Then times the weights delta x. So that is the ice rectangles, right? Ice rectangles. If we're using n, n approximating the sum of n approximating rectangles, that will be the summation, the index I starting from 1 to n, and we can let the n approaches infinity, that becomes the area of this whole region S, right? So this is direct to show that the height of each rectangle will be the difference between the function f and g. So this is the case one I called, okay? This is the case one I called. The case one I called here, okay? For all the x, the function f and g are both positive and the function f is greater than g. Now, let's see the case 2, okay? Let's see the case 2. So for this one, if we cut into n rectangles, okay? N approximating rectangles, we can write in this way. Let me write one more. So just continue the area of the ice rectangle, then we can use the summation of nth rectangles, right? Nth rectangles. F, how f is greater than? We assume that one function is greater than another. Okay, we assume function f is greater than g. Fxi star minus gxi star times the equal weights. This is the area for one approximating rectangle. Then we let the index starting from 1 to n. That is the sum of n approximating rectangles area. Then the area of this region S can be approximated by those, and we can let the n goes to infinity in this way, right? Similarly, like the one we defined in the previous section. Now let's check case 2. Okay, let's check case 2. So for all x in the AB, we still have f is greater than g, but this time my f will be positive and my function g will be negative. One is positive, one is negative. So still have the area, the region formed between two curves. And again, f should be greater than g, obviously. Okay. Now let's check the case 2. Okay, one function is positive, another function is negative. So let me write case 2 here. Okay, case 2 here. When f is, for all the x in AB, f is positive, g is negative. Now let me draw the graph and let's figure out the area of the region S. So let's form the coordinate x, o, y, and let's draw the curve. F, and this is G. So this part is my F, and let me show it's always, okay? Let me show G is always negative. So I have the function f and then the function g. Okay, this is my function f. This is my function g. And I'm going to have the from A to B in this way. Okay, from A to B in this way. So now function f is positive, function g is negative, right? Function g is negative. Then we are interested in the area between f and g from A to B, right? From A to B, so will be this region S. So similarly, we can cut this region S into n strips with the equal width, and we can take the i's. We are going to estimate the i's strip, okay? We are going to estimate the SI, okay? This one I just called the strip SI. And again, here the endpoint. This endpoint in the I subinterval, this point will be xi minus 1, and this point will be xi, right? It's the value, x values, okay? X values. So here it's again equal weights for each strip, equal weights, and that also gives the weights for each rectangle. It's the same. Delta x from equals b minus a over n. We have n strips, right? Now let's check the approximating rectangles area. here it's in the I subinterval from xi minus 1 to xi. So I can choose any value, xi star, for example, here, xi star, xi star, xi star. So this value gives xi star, okay, in the x-axis, okay. So let me just point out here. So that is xi star, the sample point in the I subinterval. Then I can take the function, I can form the height based on the xi star. So that will be the height of the rectangle, okay, of the rectangle. Then I'm going to form a rectangle to estimate the area of the strip SI, right? To estimate SI. Now, here, what is the y value here? What is the y value here? Of course, this is when x value is xi star, then the function value will be f xi star, right? It's again fxi star because this point is on the function curve f. And then this is the function curve g. Then what is the function value here? That is when x value is xi star, so the function value will be g xi star. Now what is the height of this rectangle? That will be this part and this part, right? So seems like it will be the positive part plus the length of the negative part, right? So the height, let me write it, okay? Let me write it. The height of the eyes approximating rectangle of the eyes approximating rectangle. So from the graph, it seems like it should be the height fxi star, right? Fxi star. And then fxi star, the height will be the value from 0 to here. So that should plus this one, right? It should be, seems like it should plus this length. How can we represent this length? Gxi, and we know actually gxi is a negative number, right? So from 0 below the x-axis, from 0 to here, that is gxi star, absolute value, right? So should plus gxi star because gxi star is the negative value, right? Is the negative value, so should plus this length that gives the height. Or you can write in this way, okay? You can write in this way. Actually, it's minus the, sorry, it's minus the negative value. Hold on. Since this function g is negative, since this function g is negative, right? When you remove the absolute sign. So here you will notice that that is the height, then the rectangle's area, okay? The area of the ice rectangle will be the height times the equal weights delta x. So the height gives the difference between the two functions at the sample point, evaluated at the sample point, then times the, that is the height, then times the equal weights delta x. Now what is the area of this region S? So the area of the region S, we can define it in this way. The area of the region S, so that is A, we can define this way. We take the n approximating rectangles area, right? So my index I starting from 1 to n use the summation notation, or we just call it the Riemann sum. Use the Riemann sum to represent the sum of n approximating rectangles area, and then we can let my n goes to infinity, right? So you will notice that the case 2, when function f is positive, g is negative. That is the same formula as the case 1 when both functions are positive. Okay, when both functions are positive. So let's come back here. Let's come back. So this is case 1, right? Case 1, when both function f and g are positive. That is the height. The height still is the difference between the two functions, f and g. And when we give the case 2, when function f is positive, function g is negative, the area A is still the same formula. Still, again, the height will be the difference of those two. And also we can think about this is the case 2, right? This is the case 2. And also we can think about the case 3 when f and g are both negative, okay? When f and g are both negative, and f should be greater than g. F should be greater than g. So now let me summarize those three cases. Okay. Now let me summarize those three cases. So the first case is the f and g looking like this way. From A, B. G can't be negative. G can be negative. Why? I just saw one question from Damu. So this is the case 1. We never supposed there are different cases actually, okay? There are different cases for the functions. So this is a case when both f and g are positive. This is called when x is defined between a and b. Okay, when x is defined for a and b, between a and b. Now case 2 is what we discussed. Okay, case 2 is what we discussed. Between a and b, f is positive. F is positive. G is negative. This is the case 2. Okay, f is positive. G is negative. What is the height? What is the height for case 2? We still get that the height of each approximating rectangle will be fxi star minus gxi star. It's the same as the case 1. And then here we form the case 3. Okay, case 3. So we have the both are negative. Okay, both are negative. But my function f, this is my function f is still greater than g. So from A to B, then to estimate the area of this region, so we can, this is the case when f and g are both negative, which is we call case 3. So can you check the height of the case 3 a little quick? What is the height? What is the height of the approximating of the ice rectangle in the case 3? Of course, it's still the difference between those two, right? It still should be the, if we have the xi here, if we form an ice rectangle here, so that will still be, that is still be fxi minus gxi. It's still minus, okay? It's still minus. So here the height will still be fxi star minus gxi star minus gxi star, because we are interested in the height between f and g, this part. So no matter which case, okay, no matter which case, we analyze several cases, it's always fxi minus gxi if function f is greater than gx, okay, if function f is greater than g. So that is the sum of m approximating rectangles, okay. So this gives the sum of n approximating areas, sum of n approximating rectangles area. Riemann sum, right? Sorry, it's not a question, it's a statement. So this Riemann sum gives the sum of n approximating rectangles here, area, and the height, okay? The height for the ice rectangle, using the sample point. It's fxi star minus gxi star, and no matter which case, okay, no matter about the sign of function f and g, but f should always greater than g. So this difference gives the height of the ice rectangle. And then how can we estimate the area of this region S? We let the n approaches infinity. We define it as the limit, right? The limit of n approximating rectangle sum that gives the area, which is the same, right? So we define the area A of the region S. Now, what is this region S? This is the region formed between two function curves f and g, and we assume function f is greater than function g. Okay, so we defined it as the limiting value of the sum of the area of those approximating rectangles, and we know that this part is the Riemann sum. So what is the change part? What is the change part comparing with the 4.1 area under one function curve? Let's recall, okay? Let's recall here. The area in 4.1, area under one function. Area under one function fx. So how can we define the area in 4.1? So that is the Riemann sum of the n approximating rectangle. But at that time, what is the height? That is just the function value gives the height for the area under one function curve. So the height is just the function value evaluated at the sample point xi star, then times the width delta x. That is the height for the ice approximating rectangle. Then take the Riemann sum, let n approaches infinity. Here the difference is just the height change between two curves. That will be the greater function value minus the smaller function evaluated both at xi star. So just the height part change and the weight does not change, right? So comparing those two, so the height change, the height expression change, right? The height expression change. Height expression change, and weight is the same. Weight is the same, delta x, right? Weight is the same, the delta x. So, and that is the free choice is the any value of xi star, right? And actually, especially we can choose the sample. We can choose the right endpoint according to one theory before. Okay, now let's check the definition first. The area A of the region bounded by the two curves fx and g and the lines between x equals a, x equals b. Those two gives the vertical line, okay, two vertical line. The left bounded by x equals a, right bounded by x equals b, where f and g are continuous and f should be greater than and equal to g for all the x in the AB. So we assume f is greater than g. Then how can we define the area A? So we have already write the area A as the limiting of the Riemann sum, right? The limiting of the Riemann sum. So we can define those as the definite integral from A to B fx minus gx, right? With the differential dx. We can rewrite the limiting Riemann sum, or we can define it similar like the one we did before. We can rewrite. Let me put my eraser. So the area A will be the limiting when A approaches infinity. Then the Riemann sum, the index I starting one from n. The height for the ith rectangle will be fx I star minus gx I star times the weights delta x, right? So we can define this limit of the Riemann sum as a definite integral, and we know the definite integral still means the net area, right? That is the net area, and it might be for case 1 both are positive, the net area A is positive, and for the case 3 when both functions are negative, the net area A is a negative number, right? So that is the definition. Okay, that is how we evaluated the area between two curves from A to B, and no matter the sign of those two functions. And by the way, how can we evaluate this definite integral? Fundamental theory of calculus part 2, right? Try to find the antiderivative for fx minus gx. For example, if fx minus gx is x squared minus x, if fx minus gx gives the function x squared minus x, so that is pretty easy to work out the antiderivative for this difference of two functions, right? So it's pretty easy. You just work out according to FTC part 2. You just work out the antiderivative for this part, and sorry, should be big G. Okay, big G. And we have already get experience how. Sorry, we have already get experience how to evaluate the definite integral from the chapter 4. So big F minus big G, work out its antiderivative, and it should be this whole function evaluated at A and B, right? So it's pretty easy to work out the areas. There is no problem. It's almost time. Let's take a 5-minute break. Then we will continue the examples.